Okay, so a lot of the things we're doing has to do with rotational stuff. Okay, we already did rotations before, but we have to do a little bit of review so that you refresh your memory on what's going on. Okay. So let me just make sure everything is correctly recorded here. Microphone, video, we're good. Okay, so this is the review. I'm not going to rewrite the notes. I'm going to go through it, but all the PDF files for the notes are on the D2O website. So we're talking about rotational motion. We think about an object going around a rim here, okay? And the radius of the circle is capital R. The angle is theta. Then we can talk about angular velocity. Let me turn off the zoom thing, adjusting zoom. So average angular velocity, delta theta over delta t, or the time derivative of theta with respect to t. Okay, you all know that. Then we have the angular acceleration, that's alpha, average is delta omega over delta t. And so that, for the instantaneous angular acceleration, the time derivative of omega, the angular velocity. So that's in units of radians per second, 1 per second, or radians per second squared, 1 per second squared. Radians are not real unit, so sometimes we just draw them. And then we had all these angular linear correspondences when we have a uniform acceleration. Okay, so for the linear case, we had things like v is equal to v initial plus a delta t. For the angular case, we have omega is equal to omega 0 plus alpha delta t. Right? So you could have a problem where you're solving for an angular acceleration, but they don't ask for angular acceleration, but they ask what is the final angular velocity at a certain time, so you would need to use a formula like this. And then you have the formulas for the change in the x, or in the case for the angles, the change in the theta. So we would have delta x is equal to v initial v0 delta t plus 1/2 a delta t squared. For the angular case, you'd have delta theta is omega 0 times delta t plus 1/2 alpha delta t squared. And then we have the formulas that don't involve any delta t's. We have v final squared minus v initial squared is equal to 2a delta x. Then we have omega final squared minus omega initial squared is equal to 2 alpha delta theta. Okay? And then these last formulas really aren't that useful, but you can get the average velocity is 1/2 the sum of the initial and final, and then the average angular velocity is 1/2 the sum of the initial and final angular velocities. Okay? Any questions about this rotational motion stuff so far? This should hopefully be secure because we've reviewed it a couple times already. Okay, then we connect the linear velocity v with the angular velocity. So if I have a distance radius r here, I have an angle theta. Well, okay, I don't even use the theta here, but the linear velocity v is just capital R, the radius times the angular velocity. Okay, r times omega. Remember, omega has units of radians per second, or 1/2, so we have to multiply something that has units of meters to get a speed. Okay, so v equals r omega. And you'll use this quite a lot, so omega is v over r. So when we do things with rolling, or how fast, when we do things like rolling, or how fast something's going around the rim of a circle, we'll need these formulas, okay? Any questions about that? Omega is equal to v over r, v is equal to r omega. You just put in factors of r to make the units work out right. To be honest with you, that's how I remember these formulas. Omegas don't have any meters in them. The v has units of meters, so I just multiply or divide by r to get the meters to come out right. Okay. Then we have this tangential acceleration. How fast is it accelerating around the rim? At is equal to r times alpha. Okay. So again, the alpha doesn't have any units of meters in it, so we're just simply multiplying by r to get units of meters. Now, we also had centripetal acceleration. AR is v squared over r, or r omega squared. To be honest with you, for quiz 5, we don't use the centripetal acceleration much at all, because we're talking about rigid bodies, and so everything is sort of stuck in place. We don't have to pull things in, they're already rotating, okay? They're already going around circles. So in this quiz 5, the accelerations we'll be talking about will be tangential accelerations, all right? So if you're using a lot of v squared over r's on quiz 5, you're getting mixed up, okay? It's going to be the tangential acceleration. Any questions? Okay, next thing is the cross product of vectors. A cross B is a vector, and that vector has a magnitude. A cross B magnitude is the magnitude of A times the magnitude of B. You can write that as just plane A times plane B, times the sine of the angle between them. Usually I call them phi, but it doesn't matter what I call them. Sine of the angle between A and B. So if the angle is 90 degrees, the sine of 90 degrees is 1. And this drops out, meaning it's 1, so you don't even have to write the sine of 90. Okay, the direction of the cross product is going to be perpendicular to both A and B. So if I have A and B lying in some plane, then A cross B is going to be perpendicular to that plane. Okay. Any questions about that? Anybody on that? Okay. Now then, in order to figure out which of those directions it is, whether it's this vector or the opposite going down vector, we use the cross product right-hand rule. Cross product right-hand rule is A cross B. You put your fingers in the direction of the first vector, A. Okay, so let me have a vector A and a vector B. Okay, in the plane of my sheet of paper or the screen. I put my fingers in the direction of A, then I tilt my wrist so I can flick my fingers or bend my fingers to B, and then I stick out my thumb. Okay. Everybody good with that? Cross product right-hand rule? Okay. Now, then we also have this cross product in terms of components. All right, so the actual formula for the cross product in terms of components is on the formula sheet. So you can just look that up there, or you can use this little trick I showed you in class. All right, so A is ax, ay, az. By the way, if in the problem it only has x and y components, in order to use this properly, you have to put zeros here. Okay. In other words, if they just say 1 I hat plus 2 j hat, it means that it's 0 k hat. Okay. So you would have to fill in zeros on the ends here. So now if C is a cross product A cross B, what we do is we make it rotable with 2 rows. You put the ax, ay, az. That's the first vector goes there. And then we do bx, by, bz, the complements of the second vector. Then if we want the x component, we strike out the column with the x's. And then we multiply these things, which I call the diagonal, going from down to the right. Ay times bz, ay times bz, minus the product of az times by, the off diagonal. The other two guys. Okay. Now the z component is very similar. You strike out the z column, you multiply these diagonals, ax by times minus ay times bx. But there was an additional wrinkle. If you have the cy, the y component, then you strike out the middle column. But now you have a gap between these two. Then you have to take this extra step of cycling this around to the other side. And then you have the ax, bx is over here. All right, this just gets copied over here. Then you multiply the diagonals again, down to the right. Az times bx, minus ax times bz. Okay, any questions about this? Yeah. Oh, that's what we just did. That's what we just did. The cross product is a vector with magnitude a times b times sine of the angle. Okay. So if you just want the magnitude, that's the formula for it. But if they want the vector components, this is the best way to do it. Okay. Any questions about that? Okay. Let's go on. And then we have, we'll do, the other right-hand rule will come a little bit later, the spin around right-hand rule. Okay, so now we have torque, which is the twisting sort of behavior, right? So we have some object with a rotation axis and we're twisting it, so it's like the rotational version of force, or for the angular case, the rotational case. So we have some rotation axis. Okay, so we always have to specify where we're rotating around. So this axis here, so it's a three-dimensional picture, so you think of an axis here we're rotating around, and I'm just drawing it as a point. And then the first thing you have is to figure out where the force acts. You put your pen there, then you draw an arrow going from the rotation axis to that point where the force acts. I call that the lever arm. You call that the position vector R, whatever you want to call it. That's R. And then you have the angle between F, and you have the angle between F and R. So sometimes people get confused about the angle. Which angle? Is it this angle or is it this angle? The point is you want to extend R and keep going with it. So in order to get the angle between two vectors, they really need to start from the same point. So you can think about taking this vector R and putting it over here. Okay? People get confused because they're not starting from the same point. So just think about it. I put the vector R over here. Now it's clear this is the angle between them. Okay? Now, for the torque is going to be R cross F. Okay? The position vector or the lever arm vector cross the force F. And the units is Newton times meters. So if I want the magnitude of the torque, how big it is, it's going to be the magnitude of R, that's R here, times the magnitude of F, that's just plain F, times the sine of the angle between them, sine phi. If we have these in terms of components, then we could use the component formula we just did on the previous page. Okay. So if we're rotating about a fixed axis, we can label torque direction as clockwise or counterclockwise. Okay, so this is counterclockwise, this is clockwise. If this is the rotation axis, it's going like this, okay, or like this. And this is what we call positive, or your textbook calls it positive. This is what your textbook calls negative. Right? Any questions about that? Now, there's another shortcut for calculating torque. This where we use this thing called R perpendicular. So you draw a line through the force vector, and then you find the distance from the rotation point, or the rotation axis, to this line. So you have some force vector here. Here's the rotation point. What you do now is you draw a line that pierces, that slices through that force. Okay? A line that goes through the force. Any questions about that? So in order to use this trick, you have to know exactly how to draw that line. Okay, just go through the force, and then you try to get from the rotation point, to this line as quickly as possible. And the way you get as quickly as possible is by trying to go perpendicular to that line. Okay? Questions about that? Okay. So that's what we call R perpendicular. R perpendicular is equal to the R sine of theta. Okay. And so then I can just write the torque as R perpendicular times F. Now, this trick, the shortcut, is usually very helpful when the force is actually either horizontal or vertical. And the reason it's helpful is because typically in a drawing, they give you the distances vertically and horizontally, and those measurements are very helpful for getting R perpendicular when the forces are either vertical or horizontal. But you can still use this as the formula that we had before. That's R F sine of theta. It's just that typically that's an extra step to get the angle to what you need to do. Okay, any questions? Good. Now, this is for everybody. So if you're personally not following this, but you think like everybody else is following it and you're afraid to ask questions, don't do that. Ask me a question. I'll try to help you out in class, okay? So if you are personally not following this, please ask me a question, even though if you think your friends are following. Okay, next thing, a spin around right hand rule. Okay, this is when we have something spinning. All right, this is a very good example. This is perfect. I have something spinning. Well, it's not spinning yet. Okay, and it's spinning like this. You think of your fingers as little arrows. You cup your fingers. The tips of your fingers are obviously the arrow tips. And so so you make your fingers point the same way that the fingers rotate. Everybody's following me on that? Okay. Then you stick out your thumb. That's the direction in which the rotation vector, omega, is pointing. Okay. So if I went the other way, no, keep doing that. I keep thinking I'm going the other way. So we don't go the other way. Okay. So now if I go the other way, I'm going like this. Okay. So go like this. The vector is less natural. Okay, so now suppose you're riding a bicycle. So this is, I think, in the homework somewhere, right? Or you're riding a bicycle, then obviously the wheel is going this way. If the wheel is going that way, you're riding the bicycle backwards. Okay, it's going this way. So which way is the rotation vector going? To my left or to my right? Yeah. Okay, you take your right hand, curl like this. It's going this way. Okay. It doesn't matter which way I'm pointing. Curl my finger like this, it goes to my left. Okay, so if you're riding a bicycle. Questions? So that's the spin around right hand rule works for the rotation. So anything that rotates, the angular velocity, the angular momentum, which we'll talk about later as well. Okay. Questions? All right. Then we talked about the moment of inertia. Okay, that's what I call the analog of a mass for rotations. How hard it is to start rotating an object. Just like if something is really massive, it's hard to get it accelerating in some straight line motion. For an object that has a large moment of inertia, it's very difficult to get it to start spinning around, right? So remember, if I do this, my moment of inertia is big because the mass is at a large distance. If I pull them in like this, then moment of inertia decreases. And so, by the way, when I was doing this demo, I never really explained it all that well because I was busy. But remember, if you start out like this and pull the content, you go faster. Okay? You go like this, you go down. So here, my moment of inertia is big. Here, my moment of inertia is small. And then we're going to talk about angular momentum conservation in a moment. So angular momentum is just I times omega. Okay? And so I times omega, in one case I is big, so omega is small. The other case I is small, so omega has to be big. Okay? You got that? We'll repeat that when we talk about angular momentum in just a minute. Okay. So, first of all, for a point particle, all right, so if we just have a point particle and let's say it's moving along, we can talk about the moment of inertia about this rotation axis. So we just need the distance between that point particle and the rotation axis, okay? So that distance is r, and so the moment of inertia will be m times r squared. Okay, so this is a very simple formula, m times r squared for a point particle. And so the units for the moment of inertia is kilograms times meters squared. Now we can add moments of inertia together. So if we had a system with a couple of masses, then we could say m1r1 squared plus m2r2 squared. Okay. Any questions about that? Now if we have if we have an extended body, then we can calculate the moment of inertia by breaking up all the little pieces. But for very simple cases or very common cases, we have these formulas and they're on your equation sheet. Okay. For a thin ring or a hoop, something like this, where all the mass is only on the edge of this circle, with a radius r with a mass m. If you go through the symmetry axis, so if you hear the word symmetry axis, it means you have something that's circular and the axis is piercing through the center of that circular object. Okay. Sometimes they can call that longitudinal axis or symmetry axis or central axis. They all mean the same thing. Right. Any questions? Okay, so if I want the moment of inertia about the symmetry axis or the central axis, then the answer for the moment of inertia of the hoop is mr squared about the symmetry axis. Okay. Any questions so far? All right. Then we also have a solid disk or a cylinder, all right? It doesn't matter if it's a disk where it's very, very short, or you made this thing a disk like this. The answer will come out the same as long as it's filled. It's filled in. It's all solid and uniform. Okay. So if we say in the quiz we say solid, and we forget to say the word uniform, what we mean is uniform solid. Yes, uniform solid sphere. Okay. Because we have not really done anything other than uniform stuff. Because the non-uniform stuff is very complicated. You have to calculate some integrals that we don't do. Okay, so for a solid disk or cylinder, then there's a 1/2 in front. So on the equation sheet, it's written as C times mr squared, where C is equal to 1/2. Okay. Now if we have a solid sphere, then in that case, it's solid meaning it's all filled in. It's 2/5 mr squared. Okay. In your equation sheet, you also have a formula for the spherical shell, which is a hollow sphere, but to be honest with you, we don't do too much of those. Then we also have a thin rod, so any sort of a thin object that really only is long in one dimension, and you're neglecting the width or thickness in the other directions, so it's only having this length. And if you're doing it about the symmetry axis through its center of mass, just 1 second. I just realized that I wanted to add something to the review at the end. I'm going to write some notes at the end. I wanted to do something on center of mass that I didn't do sufficiently in this review. Okay, so now it's going through its center of mass, and the moment of inertia for this rod will be 1/12 ml squared. Okay. There's a formula also in your equation sheet. If it's through the end of the rod, it actually ends up being 1/3 ml squared. Right. That's on your equation sheet. I don't write it because maybe because I was lazy. All right. Anyways, you can calculate it for any axis by using the parallel axis theorem. Okay. So parallel axis theorem says if you know the moment of inertia about the center of mass through its symmetry axis, if I want it through another axis, let's say shifted away by a distance h, then it will be the center of mass moment of inertia plus m times h squared. So if you wanted to derive what is the moment of inertia about this end of this rod here, you would just simply say, take the moment of inertia around the center plus m times h squared. So I'll shift the axis by L/2. So I have m times h squared L/2. Okay, so let's just derive this formula that I didn't write down. So if I wanted the moment of inertia about the end of the rod, it will be 1/12 ml squared plus mh squared. But h will be shifted over by a distance of L/2. Is everybody following what I'm talking about here? Okay. So then this guy goes in here, and then this will become 1/4 ml squared. So if you take 1/12 plus 1/4, you get 1/3 ml squared. Okay. Questions about that? All right, let's go on. Next topic is angular momentum. So if we have, okay, so angular momentum is the angular analog of momentum for the angular case. So if I have a particle with mass m with a velocity v, and this is my rotation point, where I'm measuring rotations, then the angular momentum is going to be, first I'm going to calculate the regular momentum, m times v, p equals m times v, and then I do the cross product of r with m times v. So this m can be multiplied at the end or multiplied in the very beginning. It doesn't matter. So if I now calculate the magnitude of the angular momentum, which has the symbol of L, it will be r times m times v, just the magnitudes multiplied together, times the sine of the angle between the two vectors, r and v. Okay. And the units are kilograms meters squared per second. Any questions? Okay, now if you want, you can get an alternative way using r perpendicular if you want. It's the same idea as with the force for torque, right? You draw a line through the velocity vector, and then you can get r perpendicular again, the distance between the rotation axis and that line. And then you can write down L as r perpendicular times m times v. It's the same kind of idea. That works because r perpendicular is L times r times sine theta. So that's a shortcut if the velocity is either horizontal or vertical or horizontal. Okay, any questions so far? All right. Okay, then we have the angular version of Newton's second law. So this is Newton's second law, F net is equal to ma. Hopefully that's seared in your memory forever. Okay, and now we are going to do the angular version of that, the rotational version. So force becomes torque. Net torque is equal to m becomes moment of inertia I, a becomes angular acceleration alpha. So net torque is equal to I times alpha. Now, we can also write this in terms of momentum. The net force, remember, we could also write as the time derivative of the momentum, with P equals mv. We can do the same thing here and say that the net torque is the time derivative of the angular momentum. It's the analog of this guy here. Any questions up to here? Everybody's good? Okay. Now, angular momentum conservation. If the net torque on a body or a system of objects is 0, then the time derivative I'm just looking up here. If the net torque is 0, then the time derivative of the angular momentum is 0, which means that L is not changing, so L is conserved. That means that the initial angular momentum is equal to the final angular momentum. And so that's why when I was doing the thing with the bicycle wheel here, it was spinning like this, right? So there was angular momentum in this direction, right? On a right-hand rule. But then when I flipped it like this, now then the angular momentum of the wheel was going the opposite direction. But the total angular momentum of the wheel and me and the stool has to still point up. So as a result, I start spinning around like this. Okay. That's how that happens. The total angular momentum has to be the same. Okay, so this is for the total initial must equal the total final angular momentum. So the idea is you add up the angular momenta of the, let's say you have particles. If you have just plain old particles, then you can use the formula r cross m times v. Okay. By the way, with a particle, you have two choices. So sometimes they get asked this, right? If I have a particle moving with some velocity here, and then I have some rotation axis here, you can actually treat this as I times omega for the angular momentum as well. You can not only get the moment inertia of the particle at a distance r from the axis, right? It's just mr squared. And then the formula would be the moment inertia, the angular momentum is I times omega. So to get omega, all you need is to get, right, so you have some velocity here, okay? To get omega, remember the formula that in omega, v and r, v over r. Right? That's actually kind of an important one. Omega goes with v over r. So when I'm trying to say I have a particle shooting across here, I can treat this as like a rigid body going around a circle, even though it's not really going, it's just a particle. But you can use the formula, the same formula that you use for an extended body. Or you can use the particle that's the particle formula for the angular momentum, just r cross m. Okay. But for everything else, for these extended bodies, L would be I times omega. So the total initial angular momentum equals the total final angular momentum. So I initial times omega initial is equal to I final times omega final. Okay, any questions about that? And if you have more than one thing stuck together, then you have to add these up for the initials, and you have to add these up for the finals. All right, next thing is the kinetic energy of rotation. So if I have an extended body, the kinetic energy of rotation is k rotation is 1/2 I omega squared. I is moment of inertia, omega is the angular speed squared. Okay, so that's the analog of 1/2 mv squared for the translational kinetic energy. Right. Now, if we have rolling without slipping, then we have the motion of this center VCM, the center of mass is CM. And then we have this omega, the rotational, the angular velocity. And so again, we have this similar, very similar formula. The speed of the center of mass will be r times omega. It's the same formula as how fast is the point on the rim going. It's, right? V is equal to r times, I keep saying it, so hopefully it's sinking in. The speed of any point on the rim is going to be r times omega. Right? Now, if I have this thing now rolling along the ground, rolling along the table, then the speed of this, the center of mass of this field will also be given by the same formula that is V is equal to r times omega. And the way you can understand that is you have the wheel is spinning, so then, I actually never did this very carefully in lecture, but when something is rotating, the top is going this way, the bottom is going that way. Everybody looking at that? But now if it's now just rolling without slipping, the center of mass is also moving at the same time, in that direction. So you can think about a combination of two things happening. The whole wheel is moving this way, but then the top is also moving this way, but the bottom is moving the opposite direction. So as a result, what's going on, if you look at a snapshot of what the motion is, the point at the bottom where it's touching the ground, it's momentarily at rest. It's not moving at all, which makes sense because that's what rolling without slipping means. Okay? The middle of the wheel, the center of the wheel is going with the velocity v, which is r times omega, but the top is actually going twice as fast as the middle. Okay? So hopefully that makes sense. You can actually think of the wheel as pivoting around the contact point. So the top is actually going twice as fast. That's actually relevant. So how many of you ride bicycles? Yeah, so you probably know this. So you're riding a bicycle, we're going this way, and your rear tire goes through a puddle of water, and notice the top of your rear wheel is going twice as fast as you are. That's why it's kicking water on your backside. Okay? It's because the water is sticking to it, and it's going faster than you are, and it's throwing water onto your back. And that's why I'm having the splash guard. All right. Then we talk about the kinetic energy of a rolling body. K total is equal to K translational plus K rotational. So we have, this is actually kind of important. So even though this seems complicated, you really need to know how to do this what I'm doing here, okay? K translational is 1/2 mv squared. K rotational is 1/2 I omega squared. All right, so it's the sum of the two. 1/2 mv squared plus 1/2 I omega squared. That's the total kinetic energy. But since omega, remember this formula again, since omega is equal to V over R, I can write the total kinetic energy. I'm going to replace this guy here by V over R squared, okay? This thing just copied it again. Then I have 1/2 I V squared over R squared. So the total kinetic energy can, if you want to just jump to the answer, it's not an equation sheet, but if you want to jump to the answer, the total kinetic energy will be not just 1/2 mv squared, it will be 1/2 m plus I over R squared in parentheses times V squared. Okay, so the additional piece coming from the moment of inertia will be a factor I over R squared. Okay. Any questions about that? So if this is a hoop, this would be m. This I over R squared would be m. If it's a disk, uniform disk will be 1/2 m. Okay. Questions about this? Yes? Top. Yeah. Yeah, doesn't matter. It always does that. Yeah. So the center of the wheel is going the same as V is equal to R times omega. So, but the top of the wheel will be going 2 times R times omega. Okay. All right. This is not, well, we didn't really cover this. I'm just telling you this because it's kind of interesting. Any questions so far? All right, everybody understand this? Because if you're doing a problem with rolling without slipping with conservation energy, if you don't know how to do each of these steps, you can't do the problem. This is a roadblock to doing these problems. If something's rolling down a hill, whoops, sorry about that. Rolling down a hill or rolling up a hill, you need to be able to do this. Okay, let's go on. That's exactly what I'm saying here. Okay, so when a body rolls down a slope, we have K total initial plus U initial is equal to K total final plus U final. Okay, so you have to take into account both the translational and the rotational kinetic energies. Then we had, let me zoom out a little bit more. Then we had equilibrium. So the main equation to apply here is that the net torque must equal 0 and the net force must equal 0. So here's an example. Let's say I have a rod with a pivot point. That pivot point will be my rotation point. Okay? So for any extended object, the first step in a cookbook recipe is to find the center of mass. And then the weight of the body acts at its center of mass. So if I have a uniform rod here, the weight will be mg, and you have the weight going straight down from the center of that rod. Okay, so if you're given the weight of the rod, you're not supposed to neglect the weight of the rod. So you just find the center and it goes straight down like that. And then what you do is you pick a rotation point and then set that the net torque is equal to 0 at that rotation point. And if the rotation point is not obvious, very often it's obvious. It's like balance on some little fulcrum or some sort of balance point or there's a pivot. Then you just use that. But if it's not obvious, then you can choose the rotation point so that one of the forces that you don't know and you don't want to calculate and you really don't want to use, you can remove that from the problem. Because if the force is acting right at the rotation point, if it's acting through that rotation point, it does not make any torque. And so it doesn't matter. You can skip that force. So one strategy is to pick a point where one of the forces you don't want to deal with is going through that point. And then for each force, you should calculate the torque it produces about the rotation point, and you keep track if the torque is clockwise or counterclockwise. And then to say that the net torque is 0, you say the sum of the clockwise torques is equal to the sum of the counterclockwise torques. Or now, well, okay, so you can do it any way you want. You can take positives and negatives, but this is the way I like to do it. And then also, if the forces are horizontal or vertical, you may find it easier to use that torque is equal to R perpendicular times F. Now, so here are some examples of where it might be easier to use R perpendicular. So if you have some angle here, you have a horizontal string supporting it, then the force is going to be horizontal. Then you can calculate R perpendicular by just drawing the line through the string, and then you can calculate R perpendicular very easily. You have the torque is R perpendicular times tau, T. But in this case here, because it's coming at an angle, it's kind of a pain to calculate R perpendicular, so it's better just to use its R times T times the sine of theta. So I'm showing you which one is the fastest way to do it. All right, then, okay, so once you've done all this, torque is equal to, net torque is equal to 0, maybe you still don't have some forces, you still have one unknown force, then what you can do is say that the net force is equal to 0, and then you can just solve for the x component and the y component, net force is equal to 0, and solve for anything you don't know. Now, I neglected to mention about the center of mass, so let me just, because this is supposed to be a comprehensive review, right? If you have the center of mass, so if I have, let's say, the x center of mass, and I have some object with mass m1 at some position x1, and then I have some maybe at position x2 with a mass of m2 relative to some origin, then it will be x1 m1 plus x2 m2 divided by m1 plus m2, and then you can do the same thing for the center of mass of in the y direction. Okay. Okay, any questions about that? All right, if not, you'll be seeing me in the videos. I'll send you an email about the details, and I'll tell you more about the extra office hours. Awesome. See you later.